Great. Very good. Hopefully everyone sees these slides. The way we're going to do this today is I think we have ample time to answer questions as they come up, and you should please just unmute and ask your question when it comes up, because chances are if you have that question, someone else here does too. No need to hold questions until the end, especially if you think it's essential for understanding the concept in the demo part, the tutorial part, which is going to be a big part of the session. So I think we can formally get started with this workshop for the Advanced Cohort Engine here at the STARR Informatics Summit. Thanks to Priya and the rest of the organizers for giving us the opportunity to show you the power of this tool and hopefully get you familiar enough that you will be leaving the session today ready to go off and build patient cohorts using ACE. My co-presenter today is Vladimir Polony. He was a software engineer in the same lab that I still work in. I'm a research scientist in Nigam Shah's group, and he is the genius behind the development and execution and implementation of ACE, and going to be co-presenting today and talking about its design and also how to use this tool.
Hello.
If you want to go to the next slide, Vlad. We have 3 simple goals for today. Firstly, we want everyone who's here to leave understanding what the Advanced Cohort Engine and its temporal query language, or TQL, are. We're going to give you the opportunity to hands-on try doing some searches using TQL. And at the end, we're going to talk about use cases for ACE and give you the opportunity to take those, take some example queries corresponding to use cases and try them out for yourself. So as far as structure of today goes, the first part, we're going to be talking about ACE's key functionality at a conceptual level to get everyone sort of level set on why we think ACE is an important tool and what it does differently. And that is, it enables you to combine the processes of electronic phenotyping and cohort building. And we'll talk about why that's so important. Vlad will then give an overview of ACE's key features, differences between SQL and the temporal query language, or TQL, and talk a little about how data get into ACE. Then we'll dive into the main part of today, which is a hands-on tutorial. We'll go through the searchable data types of ACE, the essential ACE commands, how to do temporal search using TQL, and how to retrieve patient data using the export command. And then, as I said, we'll talk about use cases at the end. Next slide. Great. So the first part, as I said, getting on the same conceptual page, ACE is a tool that lets you combine electronic phenotyping and cohort building into one process and one interface. So when I talk about electronic phenotyping, a phenotype in our view of the world is going to be a clinical event or a condition of interest that takes place at a certain time period for a certain patient in their life. The process of phenotyping is deciding whether or not that clinical event or condition or it happened using data in patient records. And when we talk about electronic phenotyping specifically, we're talking about electronic health records as the source of data for deciding whether it happened. And so here, this construct in the center of the page, Nigam talked about this in the morning session. We talk about a patient timeline. It is something that happens at a certain point in a patient's timeline. And we may need to use data around that point in time or prior to in deciding whether or not it happened. And then cohort building is the process of taking that electronic phenotype or set of electronic phenotypes and retrieving the set of patients that meet those criteria from a database, in this case of electronic health records data, the same source of information used to identify patients who met that phenotype criteria. Questions about that conceptually from anyone? Hopefully that's something that's familiar to most people here. Cool. So you'll hear Nigam's influence in this next slide. This is another hands-on activity to get us all thinking in the same way. So get out your favorite writing implement, keyboard, notepad, piece of paper and pencil. And I want you to think of a phenotype or a clinical event. It can be anything relevant to the research that you're currently doing, your favorite disease. I know that's a weird thing to have, but I certainly have a few. So think of a clinical event or disease. Take about 10 or 20 seconds, whatever pops into your mind first. And then when you have that set, next slide, write down what you would need to see from a person's record, from their electronic health record, that would make you believe that the event in question happened. Take 30 seconds or so here. And hearkening back to what Nigam was talking about in the morning, think about the sources of that data. There can be multiple modalities of data. We're not limited to one thing or one type of thing here. I'm glad you can go to the next slide. So when you've written down a set of things that you're happy with, now decide how many of those things you would need to see to be confident that the clinical event or disease or condition occurred or was present for your hypothetical patient. As in, you may have written down many things. If you go back one slide, you may have written down many things that would be useful in deciding whether or not a clinical event happened. And that might be more than what you would need to actually be confident that a person or a patient record is indicative of that event happening. There might be a subset of those. So as an example, if you want to go to the next slide, Vlad, this is the phenotype that I chose for today. I want to think about male patients who are over 65, who have type 2 diabetes, no history of stroke, and then went on to have a stroke after administering a diabetes medication, glipizide. So here, type 2 diabetes, I might think about that as my first phenotype of interest, and I might be satisfied and say, I think this person, a given person, has type 2 diabetes if I see at least 3 instances of an ICD-9 code for type 2 diabetes, 250 dot something, within, say, the last year. Or I might be happy to say someone has type 2 diabetes if they have 1 ICD code and have a record of diabetes medication, or perhaps a laboratory test for HbA1c, which suggests that their blood sugars are high. Those are all ways that I might decide that a person has type 2 diabetes based on the data I have access to. Stroke, we can do a similar thing. And then age is pretty unambiguous, as is sex or gender, at least in our EHR data, as well as timing of events and occurrence of glipizide. So the process of phenotyping and cohort building go hand in hand, because you can imagine that using a tool like Atlas, which some of you may have just come from learning how to use, or a tool like ACE, you can imagine needing to iterate on those phenotype definitions to see how adding ICD codes or adding laboratory tests changes your definition of the phenotype. If you were to take 2 weeks and try to build your most perfect, most comprehensive phenotype that you could, and then take that phenotype and implement it as SQL, only to find that there are 7 patients who meet the criteria in your database because there's only a small number of people who say have a given lab test, that's time that was spent that you now can't get back. So a tool that lets you combine phenotyping and seeing how a phenotype definition update changes the cohort you get back by executing a search really quickly is what ACE does, and it's what it lets you do. And so this process, hopefully, of thinking about a phenotype, writing down what you would need to see, and then looking at this example, I hope will demonstrate a little conceptually why we think these processes are essential to combine in one tool. If you go to the next slide, Vlad. So this is an example of, so this is a screenshot of ACE, actually, that we'll get a chance to use. And this is the set of variables that correspond to one implementation of a phenotype for that human language description on the previous slide. And the visual on the upper half shows the points in time in a patient's record, where each row here or line is a patient record, that certain parts of that phenotype definition were true. And ACE lets me iteratively update the values of these variables and see how the colored boxes essentially change in timing and number, so that I can arrive at a phenotype that is good enough for my research question. And the goal is for the end of the session that you are able to do similar types of searches and get this kind of hands-on experience using ACE. All right, we can go to the next slide. Vlad is going to talk now about some of the design overview and features of ACE.
Hello, so my name is Vlad, and first of all, we need to answer a question. So what is ACE? So as Alison said before, the ACE, or Advanced Cohort Engine, is a high-performance temporal cohort search engine. It allows users to quickly search and retrieve patients' records or cohorts of patients that meet the criteria that we can specify in the temporal query language. Why did we create ACE? Well, in SHALab, where we created the first version of ACE, we had a specific problem. We're thinking of implementing a project called Green Button, and for that one, we needed to be able to create very quickly and iteratively patient cohorts. And by quickly, pre-ACE to define patient cohort took about 2 weeks or more, because in order to define a cohort using SQL commands, you need someone who speaks really well SQL. And those SQL queries will become not very trivial after certain complexity. SQL is not really designed to support temporal queries, meaning time-based queries. You cannot easily ask SQL, give me all the patients that have event A before event B. Because first of all, SQL doesn't have a concept of a patient. Second of all, it doesn't have a concept of time. In SQL, all we have is a column and row-based information, which we can manipulate and query using the complex queries that operate on columns and rows.
If you're advancing your slides, Vlad, we don't see the slide moving.
Yeah. So what are the key features of ACE? So key features of ACE is that ACE is dataset agnostic. What does that mean? So dataset agnosticity means that in order to query ACE, you don't need to know anything about the underlying dataset. Typically, when you use an SQL, you need to know the column names. You need to know the specificities of the dataset, meaning which tables can we join with which tables to get a desired result. Also, there's some specificities in terms of values. How are null values represented? Is it a null? Is it a zero? Is it an obscure negative value? It's hard to say all of the times. So that's the dataset and schema agnosticity. The other requirement was high performance. We needed to be able to search in datasets of hundreds of millions of patients very, very quickly. And by quickly, it means writing a query in a few minutes and then executing a query in a few seconds. Just for history, we have run ACE on Truven dataset and also Optum datasets. Truven has about 150 million of patients, Truven about 65 million of patients. And the performance was basically seconds to retrieve a cohort of patients. ACE needed to support a native temporal queries, meaning it needed to understand the concept of time. So time cannot be something of an afterthought. It needs to be the main supported feature, meaning it needs to be designed in such a way that I cannot ask questions about history of events, no history of events, something before something else, something occurring at the same time as something else. It needed to support a wide range of export features. So export data into other programming languages, just Python, Java, R, or just flat files like CSV or TSV. The main issue we had that we had a lot of data sets, and ideally you would want the same query to be able to be executed on different data sets, meaning what are the results for this cohort on data set A, and very easily to be able to say what are the results for the same query on the data set B. If people know SQL, they know that it's not a trivial exercise because of the problems I mentioned before. So we have different tables that are named differently. They sit in different databases. They have different schemas, which have different column names, et cetera, et cetera. So that's not a trivial exercise. In ACE, the queries are fully portable because it has a limited set of features that you can query. Another thing that we were really keen on was a conversational mode that allows query refinement. So what do I mean by that? Conversational mode is that you can converse with a data set very quickly. You can iterate on queries, meaning I change a query and I want to have the results within a second or a few seconds. Because as Alison mentioned before, very often we create a perfect cohort. It looks great, it uses the right features, but we have 2 patients. So we need to refine the cohort and maybe relax some of the constraints to get a big enough cohort of interest. ACE supports data and feature standardization. So there's an ETL process, which takes care of loading of the data from native schema, transforming it into data agnostic schema that ACE then can search on. And that takes care of a lot of the problems of the SQL as mentioned before. Big key point that ACE supports is the hierarchical expansion using knowledge graphs. So this is one of the key areas that we really needed to support because very often when we query something, we need things to be hierarchically expanded in the proper knowledge graphs. By that, I mean, we can list maybe all the diabetic drugs and we can go to the RX norm and list every single RX norm, or we can use the ATC knowledge graph and say, give me all the diabetic drugs. In a similar way, we needed a way to map drugs to the hierarchies such as ICD-9. So if I query, let's say for diabetes in general, code ICD-9 250, I want that query to be included all the children of that ICD-9 code. So let's talk about a little bit about TQL and let's compare what does TQL do versus SQL. So SQL as a language is a generic database language that allows querying and manipulating the underlying relational database. TQL is a very specific language that's a temporal-based language and allows for querying the concepts that we use in medicine. So it has a knowledge of things like what's a patient, what's a concept death, what's a birth, what's the ICD-9 code, how do you expand it in the hierarchies, all these concepts that we use in medicine. SQL works on columns and rows. So all you can use in SQL is say in column number 1, I'm looking for value 2, and it's in the database ABC. That's all you can do. In order to support time, you need to do a complex join query that then produces a temporal table that you then sort, and it's a non-trivial exercise very quickly. TQL supports these temporal operations out of the box. We don't think about columns and rows. We talk about patients and temporal operations. SQL does a generic column query. TQL does a medical feature queries. So medical feature query would be, give me all the patients with this specific ICD-9 code. SQL needs complex joins for hierarchical expansions and knowledge graphs. As I said before, SQL doesn't have a concept of what's a knowledge graph? How do I expand in it? All of that needs to be done by SQL command. In TQL, there's a native support for that. So you don't have to worry about how do I expand this code in this hierarchy, it's already supported. So let's talk about briefly about the ETL process. So ACE ingests data directly from STARR OMAP and performs the extract, transform, load process, and it generates a time and feature index representation of each patient. So in that way, ACE does all these joins that you would otherwise have to do in SQL and generates a patient object. So imagine patient object as a patient that has a timeline, and the timeline goes from patient's birth until patient's death. And on that timeline, we can have events. So there could be medication records put on that timeline. There could be diagnoses. There could be lab results. And everything happens on that timeline. So during the ETL process, we do all these joins and convert all this disjointed data into a singular patient object. Then we make sure that data integrity is preserved. So basically we remove things like negative dates or things that happen before birth or after death. We resolve all the strange values, meaning if a data set has null values in labs represented as -3 million, we represent it as null values. We try our best to preserve the integrity of the data.
Alan has his hand up. You have a question, Alan?
Yes.
Hi, maybe we can comment on this later, but I want to ask about whether or not in STARR OMOP, sometimes the timeline of things get kind of mangled. We often think of, we've experienced personally that sort of, say for an infant, the birth weight will also have a second value that is discharge weight, but the time will be like condensed onto like the same encounter. Could you comment on sort of how do we distinguish these cases, and how are you thinking of like what the true time is and what is the like billing time, or like, yeah.
Right, so on ETL, when we perform ETL, we basically write an ETL specific to a data set where we try to address all these issues. So for instance, there are similar issues where in STARR OMAP, you have things that cannot be attributed to a time in a patient, meaning they have a date, but it's an invalid date, meaning it's date after 2022 or it's date before 1100, right? So for those, we take them out because we cannot place them reliably on a timeline. So we try our best to basically put all the events on appropriate parts of the timeline. If that's not possible, we have two options. One option is to remove it completely, as to not have someone query something that is demonstrably untrue. Or the other option is to include it with a flag that says, this is probably wrong. And then user can decide what to do with that when it's outputted.
I'll also add here that the instance of ACE using STARR OMOP means that while we have used certain processes for making a decision about when an event on a timeline is associated with a patient, the patient identifier and the source records in the ACE data will correspond to data in STARR OMOP, which will correspond to data in the versions of the source data that STARR OMOP was generated from. And so what it means is that you will always be able to link data that you output from ACE to data in STARR OMOP and potentially also to data in Clarity when you want to do something like validate the instance of a time point in a patient's record. And also, I think, Alan, what you're raising is the challenge of translating data from Clarity into a searchable object, because it's actually not necessarily right or wrong to pick a given time point and associate a value with that time point. It's more a matter of how that decision gets made for the purpose of the use case that it is applied in, if that makes sense. So in the case of a lab test and its result, for example, if we have multiple time points about when the lab test was, the sample was collected and when the value was obtained from the result of the test, which time point does it make sense to associate that within a patient's record is not necessarily one answer in every case. So I think more valuable is to be able to do a backtrace to find the additional data points that you might need for a given project. And so I think that's something we've kept in mind and enabled to the best of our ability in the sense of providing patient identifiers and timestamps. Yeah. Great question.
Thanks for commenting.
Yeah, really good question. This is again, sort of at that intersection of phenotyping and data management and search and patient data, exposure to research. Yeah. Other questions about what we've talked about conceptually before we get into the hands-on tutorial part? All right. Oh yeah.
Sorry. Since you said conceptually, I have this thing that I'm trying to understand in terms of at the very beginning when you were talking about phenotyping and you talked about there's an event or a condition of interest and you're deciding whether it happened. And since this is a temporal query language, and from my exposure to Atlas, it seems like they put almost as much focus on when it happened. And so I guess this is a question about when this, maybe there are two different notions of what is a cohort in terms of, is it a set of patients or is it a set of patients where each patient is associated with a particular point in time that's of interest?
Yeah, thanks for the clarification question. So in almost every case, and this is certainly what motivates the design of Atlas, what we mean is not only whether or not an event occurred for a person, but when in their specific timeline it occurred, and being able to return that information, and also do searches relative to the periods before and after a specific event are the main driving use cases for ACE. So thank you. Yeah, a phenotype almost invariably consists of both a set of conditions or codes of interest, and then when you're retrieving a cohort corresponding to that phenotype, when in that each person's record that event occurred. Yeah, hopefully that helps.
Yeah, thanks.
Great. So I'm going to paste a URL into the chat, and this is where everyone can be hands-on going forward during the tutorial, in that you will be able to try all of the commands that we're going to show you in our screen in front of on your own laptop. So this was the reason we needed you to complete that sort of pre-step prior to today's workshop, so that we had everything set up that let you access this URL. Hopefully most of you are able to, and you'll need to be connected to the Stanford VPN, and then you may need to authenticate with your SUNET username and password. So go there if you're interested and following along and typing in some things yourself, or feel free just to watch us demo it for you. Hopefully, 27 people using ACE at once, our instance will let it stay online, but let us know if you have any technical issues also. All right, Vlad, do you want to go to the? Sure. So the URL, so Glenna, you're typing, and never got info on ACE access. So possibly then when you try to go to this URL, you will see a screen that says you don't, will probably redirect you to a VPN screen. Is that right? Okay, so in that case, if you didn't do the pre-steps that Priya sent when you signed up for the workshop, then you should just follow along on the screen with us, and then you'll be able to follow up with Priya afterward to get direct access. The system is available to people in the School of Medicine who, in this case, for the purposes of the workshop, if they reached out to Priya in advance to get added to the necessary work group. In future, it will be a similar process to getting access to STARR OMOP DID or Atlas for you to get access to this instance of ACE. All right. I will try to be monitoring the chat, but I'm also talking. So if I miss a question that one of you has in the chat, feel free to just unmute and speak up. So the first type of command that we're going to orient everyone to in ACE are commands for finding patients who were a certain age or who had a record at a certain time. So we're going to be using this visual throughout the rest of the tutorial, where imagine this line is a patient's timeline, where the far left indicates the earliest record that we have about them and the far right indicates the latest record that we have about them in STARR OMOP. So next slide, Vlad. If we wanted to find a person who is between the age of 20 and 30 years at some point in their record, that's going to correspond to a time interval on their timeline and a search in a ACE for age 20 years to 30 years is the way that you would find people who meet that criteria. Similarly, if you want to find people who have a record between some range of calendar years, you would use the year command, and that's going to be a potentially different time interval on a same person's timeline. And you can get even more specific and search for dates using this calendar date format to find, say, between 2017 and 2020 time points in patient records. Demographics-wise, you can search for people by gender. So you can say gender equals female to find all female patients. This is a query that will return an entire patient's timeline because in the ACE view of the world, these demographics variables are constant over a patient's record. We know that that is not necessarily true. That is, however, also the assumption of STARR OMOP that these demographic variables stay constant from a patient's record. So similarly, you can do a search for a person's race. So race equals Asian, for example, or ethnicity. And these will, again, return entire patient timelines for the patients that meet this demographic variable. Death information, if it's inpatient death or from the Social Security Death Index prior to a certain point, are represented as time points on a person's record. So to Joe's point, not only do we know if we search for death whether or not a person died, but we can also retrieve the time point of that record in their data.
So let's do a quick presentation of these commands on ACE. So if you have ACE open, this is what ACE looks like. And you have a basic information about the data set. So we are searching in 3.4 million patients. There's 297 million encounters. This is just a generic information about the data set, which says we have 46% males, 54% females, 37% are white, 14 Asian, 3 black, and 46 other. And this is the age distribution. So we talked about gender, so we can maybe gender, race, and ethnicity. So let's find all the Asian. So as you can see, there's a auto-suggest that allows me to just quickly search and display all the values we have. So we can pick, let's say, Asian or unmapped concept or patient refused, and we can quickly query for those. So we have 56,118 patients which were returned in 0.3 seconds. Let's talk about briefly what we see here. So this starfish diagram, in gray, we see what's the percentage of data in the entire data set for labs. So we see about 3/4 of patients in the gray in the data set have some labs record. Compared to our cohort, which are these patient refused race, they have slightly more labs, the green one. Similarly, in our entire data set, the gray on the ICD axis, there's more records in the general population as in our cohort. So our cohort has percentage-wise less ICD-9 code. So that's just a quick way to see what data quality do we get with our result. On the right side, we see basic description. So cohort is female, mainly. It's between 19 and 44 years old. It's mostly 1 to 10 encounters spanning more than 5 years. So if we open these fields, we have actually uncovered the demographics as we saw before. So we have slightly less females than in general population and slightly more females, the green bar, then gray is the general population, and slightly less males. Everyone is of other race because that's what we queried for, 100%. And this is the age distribution. So green bars are our cohort, gray bars are general population in the data set.
We're getting just a couple of questions in the chat. So
yep.
First question from Dave. In the overview histogram, when is age as of?
This one?
So either in the, starting histogram or here.
That's when they entered the cohort.
Okay, so age at first record is the age that we use to generate that first histogram. And is that true for this histogram also?
That's the entry into the cohort.
Yeah. Great. And then Georgia is asking sort of what the difference is between the STARR cohort discovery tool and ACE. And its main difference, its purposes are similar: to provide a tool for retrieving patients that meet specific criteria. The technology underlying ACE is fundamentally different from the STARR cohort discovery tool. And it is, in essence, a tool that provides a language that enables the expression of really complex temporal phenotypes that are more nuanced than what you can easily express using the STARR cohort discovery tool. So the STARR cohort discovery tool is great for doing sort of a really quick feasibility assessment of number of patients that meet some criteria. But if you're trying to build, say, a research data set using a tool, ACE is going to enable you to do that in a more direct way, using TQL. And hopefully by the end of today, you'll see examples about what the TQL temporal query language allows you to do beyond a tool like STARR cohort discovery, and complementary to what a tool like Atlas enables as well. Thanks, Vlad.
Any other questions? All right, let's move on. So here we have a description of how many encounters these patients have. So about 80% of the patients retrieved have 10 or less encounters, which means we don't have that many data for them. And also the duration of the timeline that we have for them is 5+ years for 40%. Here we have the residual or representation of what are the codes that are overly represented for this population that are not as prevalent for the general population. So for our cohort, highest percentage of patients that in general population has the CPT code 99214, and as well as these codes. These are the diagnoses that are overly represented for this cohort that are not as prevalent in the general population. And we have a similar information about drugs and labs. Okay, we can go back to the presentation.
Great. So in addition to being able to search patient demographics, there's also commands for searching for procedures and diagnoses. So for procedures, you can use CPT equals and enter a CPT code. And this will return the time interval, the time points on a patient's record when it was true that they have a given CPT code. Similarly, you can search using ICD-10 PCS codes. So these might show up at different time points in a patient's record. And then you can do a same type of search for ICD-9 and ICD-10 codes. And here, these may also have durations that reflect the visit or inpatient encounter where that ICD code was recorded. So if a person had an inpatient hospitalization, for example, where a given ICD code was recorded, then in ACE, we will return the interval of that time period corresponding to that ICD code.
Okay, let's look it up in ACE.
Yeah, we can do a couple of examples.
So here I'm gonna also demonstrate how easy it is to ACE. Is it for ACE to handle the search? Because you might know all the CPT codes that exist. I do not. I like to search for them. So let's say I want a diabetic retinopathy code. So related to that. So I could either search it on the internet and come up with the correct CPT or ICD-9 code, or I can just...
So you'll want to search for that with an ICD code, I think.
Oh, correct. Oh, sorry.
Yep.
Diabetic retinopathy. I just search here and I see it's 362.0. And I can select anything that contains diabetic retinopathy. And as easy as that, we can get all the patients that have that. As we can see in the fraction of a second, we have the patients for that. Similarly, we can search for CPT codes. So we could do diabetes
prevention
codes,
visit, for example.
And very quickly we see patients with that. Stanford also provides ICD-10 PCS codes. So in the same way we can search here, and the auto-suggest allows us very quickly to arrive at whatever we're interested by just quickly typing ahead. Okay, we can go back to presentation.
Questions about that? Hopefully these examples are pretty straightforward, and maybe some of you are following along and trying some searches yourselves. Medication searches are similar in the type of command. We provide two ways of retrieving records corresponding to medications. You can either do a search for an RX CUI. So this is a vocabulary from the NIH National Library of Medicine for medications, and you can specify even the drug route and drug status corresponding to a drug prescription using an RX CUI. Or you can use, as Vlad talked about earlier on, the anatomic therapeutic classification system to find medications that are for a specific indication, like lipid lowering medications. You can use an ATC code to find all of the drugs that are used as lipid lowering medications. And then you don't need to enumerate a large list of medications, but you can if you know what they are and if they're specific to your study. So these are two ways that we enable searches for drugs. And Vlad, you want to switch back and show an example?
Let's look them up. So first, let's look at, let's say, glipizide. So we start with a keyword drug, and we ask for glipizide. And it came up as the first choice. And then we can do route. Let's say oral, and we can do also status. And this could be inpatient administration. So here we are searching for patients who are taking glipizide and who were, the glipizide was administered as an inpatient administration orally. Simple as that. If we want something else, we can use the ATC class of, let's say, glucose combinations or glucose steroids or lipid lowering drugs. So we can search for classes of drugs, let's say lipid lowering drugs. And as simple as that, we will have a result for this ATC class.
This is an example of what ACE does when we do a search for lots of patients here. So you're seeing how many patients it processes and how many it's found so far in doing this search. Most of the time it's too fast for us to see these numbers, but when we do a search for a class of medication that's really frequently prescribed, then it takes some time for it to retrieve all of the patients, all of the hundreds of thousands of patients. And to Mohammed's question, ACE data are refreshed at the rate that STARR OMOP data are refreshed. So if there's a new version of ACE, STARR OMOP data, then ACE is updated to that.
Okay, so we have about 1 million patients that were taking glucose lowering drugs. Okay, let's go back to the slideshow.
And we can also do a search in ACE for measurements. And this is where you'll see some similarities to the terminology used in STARR OMOP. So we can do a search specifically for labs or vitals, or we can do a search generically for a measurement and specify either lab equals some code or vitals equals some string when we're doing this kind of search. When we're searching labs, we use link codes, but again, auto-suggest based on the name of the lab will mean you don't need to know a link code to do a search for a certain lab test. And then you can also pass as an argument to the labs command or the vitals command a value that corresponds to the result of that measurement, if that's something you're interested in. So for example, patients who have blood glucose above a certain value, you can do a search for those patients using the labs command.
Yeah, so let's look at that in ACE. Oh, sorry, is there a question?
Yeah, this is Eileen. Quick question. I know the auto suggest you're typing the text and it comes back with a code, but then is there a way to keep the text with it so that you can then look back and see that and not just all the codes?
Oh, so TQL is basically based on, so representation in TQL is in codes. The reason for that is that names can change, but the codes will remain the same. So for instance, in UMLS, the code 250.50, which is diabetes, will have 10 different ways, 10 different names, right? But it has only one code. So that's why we stick to the code. And you can very easily look at in ACE, like explore, like what is this C10? You just hit control space and you see, oh, it's lipid modifying agents. So you can very quickly, but
you can reproduce it, but that's
correct.
what I was just saying, because a lot of times the researchers will need a definition to document what they included and how the query was defined. So I was just wondering if you had the descriptions to the labeling to go with it. Okay, thank you.
Evan is also chiming in, which is great, and you'll be able to see this as we get to some more advanced examples. You can actually, this box here is kind of like a terminal where you can type code, and you can actually include comments. So you can write down as a comment what the name of a drug is, and then have the variable on the next line. And so
something like this. So
yeah, annotation. Yeah, because that's where pseudocode is really handy. So you can reflect your intent even if the implementation is wrong.
Correct. Yep. Great question.
Okay. Any other questions?
So one person, it looks like they're getting an extraneous input error, which means that there's an error in your code. And if we have time at the end, we'll be able to go through and try to troubleshoot some of that. But for now, we'll keep moving. We'll keep trucking through the tutorial. So we'll come back to you, Amy.
Yeah. So let's demonstrate some labs. So let's look for patients who had A1C over 7. So we can just say A1C. And let's do
you're going to want to use with a unit. Yep.
Correct. So just for demonstration, so basically unit is included in the lab name. So here's the percentage is the unit, and or percentage of total hemoglobin. So I select that one. I'm going to do 7 and max. So basically we specify minimum and maximum value. So if you want just 7, we can do 7 and 7, or 7 and above would be 7 and max. We can retrieve all the diabetics who have a high A1C, which is 60,000. Let's see, it took 1.9 seconds. In the same way, we can query vitals. So we can just either select everyone who had the pulse measurement, or we could do vitals where, let's look basically people with high body mass index, basically obese people. So BMI over 30. This is going to give us all the people who are obese, or actually I think it's morbidly obese over 30. It's going to be probably a lot of patients. So 402,000 patients are morbidly obese. Okay, let's go back to slides.
And then there's the ability to also do some search by Stanford specific departments or by visit types, as in inpatient or outpatient. So you can, again, auto suggest will give you names of departments populated from STARR OMOP, and visit type, I believe there's 3: inpatient visit, outpatient visit, and not specified, if you're interested in restricting to those types of visits. Okay, so those are sort of the main clinical variable type queries that ACE, or commands that ACE uses. And now in the next part of the tutorial, we're going to show you how you can combine values for certain types of variables to get specific in the patients that are returned using Boolean and temporal operators. So the first type of operator that ACE lets you use is and so here we have our patient timeline again, and we have we have an example person who has some green code and some orange code in their record. And so go to the next, Vlad. If I were to do a search, and this is the syntax that you would use, and open bracket green comma orange, where you can imagine green might be an ICD code and orange might be a CPT code. It's going to return all of the patients, the entire timeline of patients who have both a green at some point in their record and an orange at some point in their record. We can do an OR search. So if we have 2 different patients, one person has orange in their record and a different person has green in their record, A search for or green, comma, orange will return both patients because there's one patient with orange and one patient with green. If they had both been the example on the top, they also would have both been returned because a person had both green and orange is also someone who has green and someone who has orange, if that makes sense. A search for not some value will return only those timelines if the person has no occurrence of that variable in their record. So not green will return the person who has orange in their timeline and never green, as an example.
Right, so let's have an example of that. Just get it sort of current. So let's look at patients who are obese diabetics. So we already have defined this BMI as obesity. And we can just basically say, give me patients who are and obese, so they're obese, and comma, another concept is going to be the lab value of A1C that is over 7. So these will be all obese diabetics.
You need a, wait, you need another bracket around lab.
Oh yeah, right. Correct, yes, sorry about that.
And you need to get rid of the equals.
Correct. There we go.
Let's see, I have a feeling, yeah, so you still need to have lab and then loing equals or lab equals.
Sorry.
Live, doing it live.
Yeah, that's what comes with it. Correct. So in the same way, we can do, let's do another concept. Let's do basically
just do an ICD code to keep it simple.
Yeah, ICD-9, diabetes. Sorry. Let's define as diabetes mellitus, which is ICD-9 250. Then we have ICD-9 250 and obesity. So these are going to be all people who had ICD-9 250, which is obesity, and also body mass index over 30. So that's 33,000. If we were to use OR, it will give us patients who are either diabetics or have the BMI of over 30. Let's go back to the slides.
Questions about that? Okay. We've also been highlighting the main functionality of ACE as a temporal query search tool. And so for each of the and, or, and not commands, there is a corresponding what we call temporal version, which takes the timing of events into account. So here, if we're doing a temporal version of and, which we call intersect, we want to intersect green and orange. That's going to return the points in time in patients' records where there was an overlap in time of the green variable and the orange variable. And that's represented as the blue sections of their record here. These time intervals with starts and ends are what are returned by this search. And this, we're also using this opportunity to introduce the syntax that you can use in ACE for assigning the results of a search or a variable to a variable with a specific name. And this is where it ends up looking kind of like a programming language. So to say I want the output of intersect comma green, green and orange to be assigned to the variable blue, you would write var blue equals intersect green comma orange, where again, green might be an ICD code and orange might be a CPT code or a medication as an example. So this is key. This is something that ACE lets you do in one line that in SQL might take you a whole bunch of lines, maybe even a page and a whole bunch of time to also execute. You can do this in a single line in ACE. We have a similar union command to the temporal, which is our temporal version of OR. So that's going to return time intervals that it was true that either green or orange were observed in a patient's record. So here we're assigning that to the variable red. And what that looks like on a patient's record in this hypothetical example is all these red intervals in a patient's timeline. And then we can do invert, which is going to find all of the time intervals that it was not true that some property existed in a patient's record. So if we do invert green and assign that to the variable named purple, that's what this will look like. It will return all of the times in a person's record that they did not see, that they did not have a record of green.
Okay, so let's look at some of these examples, and I will be using the variable, the var examples, to keep things simple, because you will see that keeping things kind of separated and simple makes things much more readable, because if they're just clumped in this big variable, they're kind of hard to read. So that's why we separate them. So first, let's define emergency room visit. So that's a visit type. And here we have
there's lots of
emergency
types,
room.
yeah.
It's 11.
Not 3.
Correct.
That is incorrect.
This is the ER. Then let's define people with AMI, so acute myocardial infarction. So we will use the command union, which basically takes, I'm looking for wider representation of AMI using ICD-9 and ICD-10 code. So it's going to be my union, and ICD-9 code for acute myocardial infarction is 410. And I want to include also ICD-10 representation. So acute myocardial infarction. So now this union represents all the time intervals for those patients that I'm looking for that had either code ICD-9 410 or ICD-10 I21.9. For me, they are identical. And now let's look at cases that were actually more serious. So patients who were intubated. So that will be CPT code. I had to look it up. Intubated is 31500. So you can also search like that. So now let's put it all together. We're looking for patients who had an emergency room visit. And at the same time, during that emergency room visit, they were diagnosed with acute myocardial infarction. And also during that same visit, they were intubated. So let's use the intersect command, and we put how you refer to variables just using the $sign. So $ER, and we want to intersect that with AMI and intersect that with the time when they were intubated. If I typed everything correctly, we have 11 patients. So basically 11 patients were in the ER, and at the same time as they were in the ER, they were diagnosed with acute myocardial infarction, and at the same time when they were in the ER, they were intubated. So let's go back to the slides.
So Michael is asking a great question. He asks, can you say more about the concept of truth over time? E.g., if an A1C value is 7.2 on the 1st of January 2020, and that was their first A1C value of 7 or more, when does that cease to be true? So yeah, you want to take it? Go for it.
Sure. We record things in ACE exactly as they're presented in the OMAP CDM database. So measurement is a point in time, and basically for me, on the patient's timeline is going to be represented as a time point. So here's where we actually, this dovetails into the history of, we can, for instance, consider that diabetes is all the time after you had the first mention of that particular high measurement. So from that time on, I'll consider you to be a diabetic. So you can use that as a first mention, or use the command of history, of which we will talk about right now. Do you want to?
Yeah, this is actually such a good question to ask. And sort of generally, what I would say here is that ACE lets you decide what that truth is for yourself. So we record in ACE the time points that variables were observed or that properties were observed in a person's record, but then you can define a variable for yourself to say, diabetic is going to be the time interval from the start of that high value forward in time for the rest of that patient's timeline. And so you do that using history of. But first mention is also an important command. So here, if we ask for the first mention of green in a person's record where there's 3 records of green, that will look like, if you go to the next slide, this one instance here in teal. So we find the first time that it was true that green existed in a person's record, and that's their first mention of green. You don't need to know when in a person's timeline that occurred. You can use the first mention command and it will find it for you regardless of the calendar time that that event took place. Then you can use history of similarly to say, I want to return the interval starting with the instance of green. So here, the yellow time interval in this person's timeline is the time that it was true that they have a history of green. So if we're talking about this instance of A1C greater than 7.2, you could choose to say, I want to return all of the time in a person's record starting when they had a history of this value of 7.2. And you would use history of for that.
So maybe
Glenna,
I present,
yeah, go for it.
Yeah, maybe let's look at the history of as an example.
Oh yeah, sure.
So let's look at patients who have a history of smoking and for which, and some codes that are intersecting with that. So let's define smoking, and that's a SNOMED code. We can use the, let's say smoking started. And then we can do, so if you specify history of smoking, everything that we intersect with this is going to be patients who had a history of smoking. We intersect, let's say, with cancer. Sorry. So these are going to be the patients who started smoking. And at some point after that, they got cancer. So neoplasms in general. So we have 570 patients recorded who have the starting of smoking, history of smoking, and sometime after that, they got cancer.
I'm sure some of you are looking at that low number and being slightly skeptical. And this is also where the source data come into play. So smoking status is actually hard to capture accurately in our STARR OMOP data. And so this is one SNOMED code about one property of smoking, just in case you are curious about why it's only 570. Yeah.
Okay. Let's go to sequence.
Questions about first mention or history of conceptually? I see Glenna asked, transient conditions like gestational diabetes. So a search in ACE for an ICD code will return all of the time intervals where there is a record or a visit associated with where that ICD code was recorded. So you can imagine if we're talking about GD, a person who has had multiple visits where that ICD code was captured will be returned, all of those time intervals for all of those visits will get returned by a search for that ICD code. And then you can choose to define, more broadly, you could choose to say, I'm going to try to identify the whole duration of a person's pregnancy, and then I'm going to identify the start of GD as in the time interval in their record that intersects with pregnancy and that ICD code, and look forward 6 months and call that their gestational diabetes interval. It's really flexible in ACE how you can choose to define these variables based on what's present in the source data. In brief, though, the source data typically will have a narrow band in time that a given ICD code was captured in a person's record. And so how you then choose to operate over that time point data is going to depend on your use case. Sequence is sort of the superhero of ACE, in my opinion, because it's the magic command that lets you look for events in a specific temporal order. So you can ask, find me all of the patients who had a sequence of orange and then green at some point in their record. And you'll notice that the sequence command uses an asterisk. And here what that does is it specifies to ACE the time intervals to return from sequence. So here I can say I want back the green time intervals from the patients who had a sequence of orange and then green. And so that's going to return these two pink intervals on the next line. Or I can put the asterisk beside the orange variable, which again could be an ICD code or a medication record, and say I want those back from sequence. And that would return the blue time intervals here. I could also, I'm not showing this here, but we could put the asterisk beside both and then you would get back both. So this is, I think, the powerhouse command of ACE there are ways that you can more specifically define the amount of time that can have elapsed between two events. So you can say orange and then green, where the green was preceded by orange by 6 months or less, to find events that are 6 months from each other. We're not showing that here, but if we have time, we can demonstrate an example.
Correct. So let's look at some sequence. So we talked about patients who are obese. So let's look at the things that happen to them later on. So obese we defined as vitals of BMI over 30. So let's look at whether they have acute myocardial infarction, let's say. So we define that. And we define it as, we used union before, of ICD-9 acute myocardial infarction and also ICD-10. So let's look at sequence. So we're looking for people who became obese, and after that, they got acute myocardial infarction. So it's simple. Sequence of obese and AMI. And let's return AMI. We'll see how many patients are that. So we have 2,085 patients for which we know that first there was a record of their BMI being over 30. That was followed by acute myocardial infarction. And just to demonstrate a conversational approach, let's put that towards patients who are morbidly obese. So I think that's over 35. Is that number going to be higher or lower? Let's see. So you have 901 patients who are morbidly obese and had AMI. So that's the conversational approach. Let's say I want to see, well, this is not enough. We have to include patients who are just overweight. So we play around, put 25 or over, and we get a different number. So conversational approaches, we can quickly have a turnaround and see these numbers change in real time. So that's the sequence command. And I believe we have a few more slides. Correct. Yes.
Just 2 more slides. So the last feature search type of ACE that we are command in ACE to go over is how to get data out of ACE once you've defined a cohort using phenotypes and you're pretty happy with it. So this is the export command. We're going to ask you to be judicious in your use of export during this demo because it writes to disk, and our disk size right now isn't super large on the server that ACE is running. So to keep it up for everyone for now, only run export on a cohort of like 100 patients or less, depending what you're doing, or don't try it at all for now. But in brief, you can output for a specific cohort that is the first thing you would specify. You can define the features that you want it to export for you from ACE. So as an example, you could say for all of the patients where there is some occurrence of ICD-9 equals 250, I want to get out their ICD-9 codes, their ICD-10 codes, and their demographics data. And this is going to actually output a CSV file, a comma-separated values file that you could read in to R or Excel that contains all of the ICD-9 codes and ICD-10 codes and the time points in a person's record where those codes were observed, and also the demographics, so things like race and gender and ethnicity as captured in STARR OMOP. You can be more specific in how you use the export command to say, only for patients during their inpatient visit, after if they had ICD-9 equals 250, give me all of the medications in their record during all of their inpatient visits. And it will output a CSV file with that information. You can also specify the start point in the export command. So here you can say for all of the ICD-9, for all of the patients who have an instance of ICD-9 equals 250, where the start point of the output is their first medication record, return to me all of the ICD-9 codes, ICD-10 codes, and CPT codes, for example. And so this is really flexible. Yeah, John is asking whether the exports are de-identified. So this instance of ACE operates over STARR OMOP DID. And so the patient IDs that are output are the patient IDs from STARR OMOP. If you have an IRB protocol that lets you link that back to MRNs, then you would be able to work with someone like Priya or other folks in RIT or TDS to do that linkage back to MRN. Yeah. What were you going to say, Vlad?
Just to underline one point that was asked before. So cohort and phenotype is something that is present in time. There's some sort of, it's not just what, but also when. And here in export, there's a very nice way to output those times when it was true by using this convention where we can define a name in apostrophes and say, this is my phenotype, and then have your phenotype definition here. That's going to be then outputted with your phenotype name, and you can do as many of these as possible. So basically, it's a very flexible way to name things, output things, and output things like phenotypes, cohort definitions, exit from cohort, entry into cohort. And since it's going to be in your CSV file, process it further, either in Python, Java, and also there's a package in R which allows you to very quickly query ACE and produce the appropriate data frames.
Yeah. So that was the sort of slide component of today. We have examples of use cases that we have used ACE for or that ACE can be used for, and we've captured them here in a Google Doc, in Google Drive. I've just pasted that. Oh, sorry, I did that as a direct message to the last person chatting with me. I'll send it to everyone. Here we go. You should be able to access this file if you are logged into Google using your Stanford credentials. And this document has sort of a written overview of everything that we just presented to you in the form of slides. And then the last section, use cases supported by ACE, has these 5 types of use cases. And we also write about them in the ACE paper, which I believe is linked in the workshop description. But in brief, we have used ACE for offering the green button service and Atropos that Sora presented on in the morning. Every consultation that was done for the green button project or that is now done via Atropos uses ACE to retrieve patient data, and even in some cases to do some of the analysis of patient data. So the first example under the use cases is a real set of variables that we had to create for a consultation as part of the green button project. And you can take these, all of these queries and paste them into ACE and try them out. Quality metric reporting, clinical trial recruitment, so identifying patients that meet clinical criteria that might make them eligible for participation in a clinical trial, generating labeled training data. All of these are really instances for specific use cases of phenotyping and cohort building. And because that is what ACE is designed to let you do, you can very quickly write queries using TQL to, for example, get the rough numbers for a quality metric. If we look at that example, there's a HEDIS measure that tries to count how many times antibiotics are inappropriately used when treating bronchitis. And that needs a set of ages, a set of ICD codes, a set of medications, and then to combine them in certain ways using intersect and union and also sequence to find those patients, for example, who had bronchitis and then were treated with antibiotics and didn't have a history of any specific other diseases and so on. All can be executed in an ACE query to generate a numerator and a denominator, which are basically what you need for any type of HEDIS quality metric, for example. Clinical trial recruitment, similar type of process. And so in this document, we just provide examples that correspond to these use cases, and you can try them out. We have 2 people asking in the chat about API access to ACE, which Vlad is the right person to answer that question.
Correct. So there is a native support for Python and Java, which you can get added to the repository and download that, but it's very simple. It's you basically connect to ACE instance, and you can just write TQL and get all the data in either JSON's format or as a object in Python that you can query them further. So you will be returned patient objects, and each of those patient objects will have things like, here are all the ICD-9 codes with all the times, here are all the medications, and then process them further. And in R, the API is very simple. It's a package called ACE, and that package allows you to say, here's my ACE endpoint, and here's my TQL, and it will return a data frame with all the results natively.
And then for people who are asking about specifically the query language specs, that is available as an appendix to our paper, which I also just linked, that describes ACE. So there are a few different ways that you can get access to technical documentation. And then if there's information that you can't track down, please email us or Priya, and we will be happy to work with you to get access to what you need, because ACE is now available to anyone in the School of Medicine to use. So I think with that, this is like sort of the end of our structured content. We have 25 minutes of open time now for more questions, or if there are people who've been trying out queries, we can hear some of your examples, have just general discussion as well. Thank you so much for sticking with us and listening, and hopefully this has given you some early exposure and familiarity with using ACE to write variables corresponding to phenotypes and patient cohorts.
Yeah,
happy to take more questions.
Hopefully we conveyed the fact that ACE does something, does it not that in a not very difficult way, and TQL is not this scary programming language that looks like, you know, something terrible. It's actually human readable. And in SHALAB, we tried this experiment, like how long does it take for someone who knows nothing about ACE or TQL to be able to start writing proficient queries, and it was generally about a few hours. And we have a tutorial material that allows you to do that very easily.
Other questions or feedback or anything like that from folks who are still here? So Alan is asking for a tutorial link. I think the right place to start is this documentation that we linked above, but Vlad, did you have another specific document that you wanted to share?
I can set it later on. It's on Google Drive, but we created a training material, yes, that we can share.
So if you actually can share all of that with me also,
yeah,
I will, because we will, you know, all of these recordings will be made available on YouTube, and it's okay with you, right? If this recording is available on YouTube as well.
Yep.
But it'll be nice if that has these links with it. So I can definitely, we can do that.
Right. So I, just from a user perspective, the links should be kept to the Stanford community, right? Because this instance of ACE is only available
absolutely.
in School of Medicine. Yeah. But absolutely, we will share this additional tutorial documentation, and then you can add it to the folder that all of this other content is in. Yeah. Absolutely.
So the YouTube will be viewable by anybody.
Sure. Yep.
But yes, all the links only go to like, yeah.
Glenna is asking, whether we can combine ACE datasets with others like Atlas or Stride. And absolutely, it's possible in the sense that patient identifiers, thanks to work by people like Priya and Garrick and TDS folks, are linkable across datasets. So a patient identifier that you retrieve using a search in ACE will be able to be linked to patient identifiers that you retrieve using an Atlas, the Atlas tool, or the Stride tool as well. Yep, because they all read from STARR OMOP.
Seating program is copyrighted by the Board of Trustees of the Leland Stanford Junior University. Please visit us at med.stanford.edu.